All right. So with that, I'm going to transition us into our next topic for the evening. Just so you know, Paul, we are 5 minutes behind, but I think that's okay. We can go 5 minutes over if we need to. So the next portion of the meeting, we're transitioning from some stories to more technical information. But tonight's presentation is going to be given by Paul Fuglevand. He is an outside technical consultant with Dalton, Olmstead, and Fuglevand, Inc. He's going to be presenting considerations for cleanup design and challenges at the Portland Harbor Superfund site. He has a ton of experience that he will be speaking to as he opens his presentation. He has about 20 minutes of slides. So I'm going to ask if you have questions throughout Paul's presentation, you can go ahead and put them in the chat and I'll start moving them over into the queue for myself, or you can just hold them verbally until we get to the Q&A portion. And then we'll use hands up and taking yourself off mute and whatever is in the chat to begin answering them in the 10 minutes for Q&A. If we don't get to all your questions in the 10 minutes, which we expect might be the case, please don't worry. There is a breakout room available between the 7 and 8 p.m. that's open for an entire hour if you want to go talk to Paul and ask him more questions, or if we don't get to your question, please just join the breakout room to get answers. So with that, I'm going to go ahead and pass it over to Paul, and he will be running his slides for you all tonight. And Paul, we see your screen, so great job. Got that going. Looks like you're off mute.
Okay, is that working there?
Yep, we can see you and hear you and see your slides. Thank you.
Oh, great, great. So again, my name is Paul Fuglevand. I've been involved in these sediment cleanups for most of my career and have been involved in sites throughout the country and have been the lead on design for sites in Oregon and Washington and Utah. I was also had the opportunity to work on the Hudson River site in New York. I've been doing involvement on that. And over the years, I've also participated with the Corps of Engineers and others in preparing guidance documents for sediment remediation. And so I was asked, just share some of my perspective on some of the issues with sediment remediation. And the first thing I did was I met with the steering committee. And so I asked the steering committee, what are your questions? What would you like to hear about as far as in this short amount of time? And so the first question was, how do you prepare for earthquakes? Because Portland is certainly in an earthquake prone area. Another question was, how do you get from doing those sediment cores that we've seen to a full dredge plan, and what kind of coring programs, follow-ups do you have to do? And then the final question was, what does done mean? When you're doing remediation, how do you know when you get there? How do you know when you're done? And then I think Sarah asked the question, what do engineers look like? What do you do? And so I won't get to that here, but we can look at that in the breakout session. So the first, earthquakes. How do we prepare for earthquakes? Well, this is an image of what's called a time history of an earthquake. It's about 30 seconds long from the beginning to the end. And in the first 15 seconds, you can see the squiggly lines are higher and lower. That's the intensity of the shaking. So this is what kind of the ground shaking looks like during an example earthquake, a time history. And for Portland Harbor, EPA has established that when we do earthquake design, we look at a 475-year event. And to put that into perspective, we often talk about a 100-year flood. Well, instead of designing for a 100-year event, EPA's guidance is we're going to look for a 475-year event. And what the seismologists and the earthquake engineers are doing in the Portland area, they've mapped numerous shallow faults that are historic and some are active. They've also, know about the deep subduction zones and all the earthquakes. And so what they will do is they will use all of that information and will develop basically a design earthquake, a design time history, actually multiple time histories, to then use in their modeling for the potential impacts of earthquakes at a site. And so they will develop parameters for the intensity of shaking, the duration of the shaking, and what the overall shape of those curves look like. Once they have that in hand, then they have numerous different computer models where they can look at how the ground is affected. And this is just a simple cartoon of a cap over some contaminated sediment. And they can look and see from their models, will the cap be disturbed and moved, or will the cap be moved enough to uncover contaminated sediment? And if that is the case, then the next step is to look at how can we modify the design of a cap over contaminated sediment to improve stability, or there may be cases where it's not practical to cap because of seismic. But if it is capped, there will still be a contingency plan that involves monitoring and trigger criteria. So this is a picture of a cap on kind of the bottom of the riverbed. The other issue is if we're looking at building caps on the side slopes of the river, again, the first thing we can look at is whether or not that cap material is disturbed and moved during an earthquake and exposes the contaminated sediment. But the other very big issue is the earthquake big enough to cause a landslide that would basically carry and disturb the whole cap and contaminated sediment? So that's just a quick summary of the type of engineering that's done to look at cap of contaminated sediments to really get an idea of whether or not it's a good idea to cap sediments and where it'll work in the Portland area. So the next question that was asked is, how do you get from your core samples to a dredge plan so you know you're going to capture the material, the target material you want to remove? And again, the first thing we do when we collect these cores, and again, these cores are often like a long aluminum tube, maybe 15, 20 feet long, that's driven into the riverbed, and it's taken out and split open, and we collect samples every foot of the core. And that's another guidance from EPA. We want to have enough samples so we have a good characterization at depth. Then they send those samples to a lab for testing for the chemicals that are in the rod. And from that, they come up with what's called the depth of contamination. And the depth of the contamination is the deepest contamination in a core. And the example here on the right, we can see the sample results that are shaded red are above the rod criteria. The ones at a greater depth are shaded green. They're below a rod criteria. And so we come up with what we call a depth of contamination in this example of 4 feet. So that's the starting point from a dredge plan, because when we're doing dredging, we want to remove the sediment that's above the criteria. And so we have at this particular core, we've measured that the depth of contamination that we would want to target with a dredge plan would be at 4 feet. So on a site, there will be lots of cores collected, and each one of those cores, we will measure the depth of contamination. And in this kind of cartoon example, the white circles with the blue dot, at all of those, the depth of contamination was 0. So we were kind of in a clean area. But we had basically a depth of contamination along this locale that was at 6 feet. And so a starting point with just one point that's maybe contaminated, but several others that are clean, we can run some models to kind of interpolate between the locations and get an estimate of what the depth of contamination might be at this area. And for example, in this example, the red is greater than 5 feet, the orange is 3 to 5 feet, the yellow is 2 to 3 feet, and the green is 1 to 2 feet. So that might be the first sampling event that we do, but we still have some questions about, do we really know its extent? So we may come back and plan a second event where we'll do some additional coring to really start to refine and sharpen the edges so we have a better idea before we move on of where the extent of that impacted material is. So one of the questions that are faced by performing parties are, when do you do those more cores? Do you do them before dredging and spend the time in the design phase, or do we do it after we've done the initial dredging and go back and do some additional cores? I've had a chance to work on a couple of the large PCB sites in the country that I think we've learned some good lessons. The Fox River site in Wisconsin, I think it is one of the biggest PCB cleanups in the country. The very first dredging season, when they went out and did dredging, they found that they ended up digging a lot of clean material because some of the extent that they had mapped with wider space cores was actually clean. And so they went back subsequent year and did a lot more cores really refined the extent of the depth of contamination and had a much more efficient removal. So in that case, not enough cores meant too much material sent dredged and went to the landfill. The Hudson River site in New York kind of had the opposite. After that first year of dredging, when they went out and they dredged to where they thought the bottom of the contamination, went and tested it and found out it was still there, went and dredged some more at the same location, it was still there, and eventually learned that they had to go back and do much more intense coring program before they were able to move on and have a good confidence of where it was. And so the lesson learned from my perspective is that it's good to do more cores before dredging, and maybe sometimes it's maybe not just one event, or maybe it's 2 or 3, even 3 events before you really get a good map of that depth of contamination. So once we have this depth of contamination map and kind of the color gradients, we then want to now develop a dredge plan. And so this is a cross-section kind of cartoon. Imagine a piece of cake and look at the side of it. So we're looking in, and the brown is in essence the frosting on the cake, in essence, in that slice of the cake, and the gray is clean. And this, we've done enough cores to have good confidence of how deep that contamination is across the site. And so this reflects maybe a fairly intense sampling program, and we have a good idea of depth of contamination. Now we want a dredge plan. Well, dredges aren't perfectly accurate. They don't dredge to the nearest inch. An excavator dredge might be accurate to 4 to 6 inches. A clamshell, a bucket on a cable might be to a foot. So the first thing we do in developing our dredge plans is we basically shift the target elevation down to what we call the design dredge elevation. So we've added this 6-inch or to a foot cushion below where we knew the contamination was as our starting point to develop a dredge plan. Then the next thing we do is realize that usually when you're dredging with mechanical dredges with buckets, every bucket footprint, cuts at a fairly straight line. And so now we want that straight line that we cut to be below the deepest contamination. And so this first bucket you can see on the right, we set the elevation for that at the lowest point of this black dashed line, which is a red dot. And we do that for every bucket. We calculate what the deepest black dashed line is. And so in doing that, we get basically a design elevation for every bucket in the dredge plan. And you can see those bucket cuts are considerably below the red line, the depth of contamination, because that's what's involved in a dredge plan to make sure we're capturing all the material. So this is an example of this is a dredge plan using a precision excavator from the Duwamish that we did. And basically every bucket footprint had an assigned elevation for it. You can see all these. This is a minus 6.7, minus 8.5, minus 9.9. So every bucket in this dredge plan had an assigned elevation. And this is a cross section again, looking at that same area. And you can see these stair steps because every bucket had an elevation assigned to it. And what we found is when we go through all these steps, we spend a lot of time doing cores to map depth of contamination. And we put an allowance in for dredge accuracy, and then we set an elevation for each bucket. We've been successful in removing that target material and not really missing anything as we move ahead. So that's just a quick, again, I'm going kind of fast just to cover the questions that the steering committee asked. The next thing is, so how does all this then get into a design? Well, the first big deliverable that is going to come out is called the 30% design. And so the questions are, well, what is a 30% design? But I like to put it in context of if you're going to build a house, the 30% design is like the sketch that you lay out of what you want to do, kind of the hand-drawn one that shows bedroom, living room. It's the basic floor plan. It doesn't have materials, it doesn't have plumbing, but it's the basic concept that you work with in order to establish the final plan that you're going to have for your house. Well, it's the same thing with 30%, for a remediation. It's an initial kind of blueprint of where we're going to dredge and where we're going to cap. It kind of reflects the engineering we've done. Do we have a good idea that in the earthquake it'll be stable? What about all the criteria in the rod? It allows us to kind of check the criteria for our design before we getting into the real refined parts. The other part about a 30% design is what we call the specifications. Specifications are, I like to say they're analogous to, you know, assembling those Christmas Eve toys where some assembly is required. Well, the specifications are basically assembly instructions for doing remediation, and they can often be, you know, 100 pages or more. At 30% design, it's basically going to be an outline of what's going to be in those specifications, but maybe not a lot of detail. And then EPA may have other supporting documents. So again, the 30% design is, again, this basic floor plan of where we're going to do the different technologies. And then the next question I thought was a great one is, you know, what does done, how do you know when you're done? And EPA has done a good job in their most recent release of their guidelines and considerations of the monitoring that's going to be involved to make sure we know when we're done and when we're not done and when we have to do more. And they've broken it into 3 phases during the remediation of the project. First is construction monitoring, and then we have remedy performance and remedial action objective. And I'll explain each one of those briefly. So construction monitoring is, was a remedy constructed as designed? I mean, if we said we're going to dredge a certain depth, we go back out and we'll do surveys to see, did we dredge this depth to the depth we planned? And did we get all of the material? And so the EPA has specified that after dredging, there will still be coring to go back to the dredge area and go outside of the dredge area and make sure that all of the target material was captured. And if it wasn't, then there's a need to go back and do more dredging. So there's some very specific and focused programs after, for example, dredging to make sure we got it all. And the same way with caps. You know, you go out and measure, did you put the thickness of cap you said you would? Did it get it to the right location? Do we have the geometry that we wanted? Then performance monitoring is now after you've done the remediation, how is it performing? And again, if we've dredged it all, then there's not as much to monitor there. But if we build caps, are the caps performing as they were designed? Are they containing the sediment? Are they containing pore water? Are they basically protecting the benthic communities as designed? So we'll do a design, we'll build, and then go back and we monitor to make sure that it is performing. And if not, we modify. So the types of performance monitoring that's been identified, one is pore water, you know, extracting pore water out of the caps, just make sure that there's not groundwater movement, pore water movement through the caps, testing the surface sediment chemistry to see if, you know, there's any accumulation of even outside sources of sediment. And again, surveys to make sure the cap is stable, that it's staying in place. So again, that's the piece of performance monitoring. And then finally, there's, you know, the whole ROD was built on remedial action objectives, a whole list of very specific objectives that are the reason why we're here. And so the monitoring will also be explicitly towards, are we achieving the long-term objectives that were set forth in the ROD? And they support 5-year reviews, you know, and other analysis. And so again, some of the main types of data that will be collected will again be surface sediment, pore water, and surface water that we have criteria for in the ROD, and to see if it is, if the overall remedy is performing as intended, and if so, great, and if not, then we adapt. So that is just, again, kind of the 15 minutes of presentation that I had, and Anna, you want to open it to